see people are still trickling in, but we're going to go ahead and get started with our next session of speakers. Next, we have Dr. Karen Stockstill-Cahill. She has a bachelor's in physics and master's in geological sciences from Michigan State and a PhD in geology from University of Tennessee. She did a postdoctoral fellowship at the University of Hawaii, where she conducted analysis of infrared spectroscopy of lunar and Martian features. She's expanded that so her background is in mineralogy, petrology, and remote sensing of Earth, Moon, Mars, Mercury, and asteroids. So she's got a broad background on mineralogy of all these planetary bodies, and she is currently the Lunar Simulants lead here at Johns Hopkins Applied Physics Lab Lunar Surface Innovation Initiative. In this role, she leads efforts to assess lunar simulants, and she interacts with NASA Lunar Simulants team, and she also provides guidance on lunar simulants to NASA and the community. Thank you, Karen, for coming and speaking to us.
Sure, absolutely. I'm going to share my screen so that we can do my presentation. Hopefully I can do this correctly. Going a little slow, sorry. There we go. Can you guys see everything?
Yes.
Okay.
Yes.
Okay, so today I'm going to talk a little bit about lunar regolith simulants in the context of what I think might be important to excavation and construction. So our goal with lunar simulants is to simulate the lunar regolith that we have on the surface of the moon, and that's based on some Apollo samples of the lunar regolith. We don't have a whole lot, and we only have near side, but we use that to extrapolate to what we think is probably pretty well representative of the surface of the moon. So there's two main types that we use, including the Mare basalt lunar regolith simulants. They have a basaltic base, and so the associated mineralogy with that, they're very iron rich, and a lot of that iron is nanophase iron, native iron. And they're also kind of glassy. They have a glutinate because of all the space weathering that's going on. We also have Highland Stimulants, and these are dominantly anorthosite. The anorthite that makes up, that's a plagioclase rich rock, and in particular, the plagioclase is the anorthite end member. So they're pretty calcium rich. They also are iron bearing, especially the ferro and anorthosites. And so they have a lot of space weathering nanophase iron as well. And they, of course, have agglutinates. And so I think the important thing to remember is that nothing is going to be pristine on the surface of the moon because it's unprotected by atmosphere. And so everything is mixed vertically and laterally by the micrometeoroid impacts. I just wanted to remember to point out that the iron is reduced. So there's not very much iron 2+. It's mainly native iron, unlike what we have here on Earth. And we have a lot of processing by micrometeorite impacts and by solar wind processes. So these are contributions that we wouldn't necessarily see in terrestrial rocks. So I'm going to simplify this a great deal. This is not really representative of all the thought and research that goes into creating lunar simulants. So my lunar simulant providers out there, I'm watering this down, I acknowledge, but we basically have a basic recipe that most providers use, which is to combine the anorthosite, which you can see there in the top right pictures, a typical anorthosite that's used here on Earth. That's the White Mountain anorthosite that's provided by Hudson Resource Incorporated. It has about 82% plagioclase with an average AN number of 84. So that's the calcium rich end member. Another popular one is the Shawmere anorthosite complex in Canada. It has similar levels of plagioclase and plagioclase compositions. And we would combine that with some sort of glassy basalt or basaltic cinder. the major components, oh, I forgot to mention that the major components in the north side are plagioclase, pyroxene, and sometimes some quartz. There might be some other mineralogy present in minor amounts, but I'm not going to worry about that here. We will combine all that with glassy basalt or basaltic cinder. The major components are glass, plagioclase, olivine, and pyroxene. And an example of that is the Miriam crater basaltic cinder. There's a picture of that in the bottom right. That's what JSC1 is made of, and that's another popular source for the basaltic. And then there are other lunar specific constituents like agglutinates, which have to be made in the lab and then combined with the simulant. And sometimes a magnetic response component, especially for the Highland Stimulants, because the ones on the moon have iron, whereas the orthocytes here on Earth do not contain very much iron. So some of the things that we think are important aspects, including for excavation and construction, are mineralogy, grain size distribution, grain shape, and lunar specific properties. So I'm going to start out talking a little bit about mineralogy. I have a nice SEM compositional map here on the right that shows basaltic fragments in sort of the green hues and plagioclase in the blues. And so we can try to match that mineralogy, but we're never going to match the composition perfectly, just because terrestrial minerals have formed under oxidizing conditions relative to the moon. So it has a lot more Fe2 plus and a lot more Fe3 plus. It's also going to have weather alteration of the minerals just based from sitting out on the surface of the Earth. And they've reacted with the atmosphere. So there's some basic differences that are going to result no matter what terrestrial rock we use. We also look at grain shape distribution. And you can kind of see what we're comparing it to. So the black line here in this plot that goes down the middle here, that's an average lunar soil. And so we want to try to match that grain size distribution as well as possible, because that's going to affect you know, how the regolith is moves, and a lot of different geotechnical properties. And so a lot of times we will look to see if we can match sort of the median sieve size and also sort of this grain size distribution. Another important thing is to think about grain shape. I know a lot of basic models start with a sphere, and you know, the lunar samples just aren't spherical at all. So this is sort of the aspect ratio we have for some of the regolith samples. And that's basically calculated by doing the short axis over the long axis. And so this grain in particular has a aspect ratio of 0.7. And so grains are really just not very spherical at all. You can see that we're pretty far off of, so a spherical one would have a value of 1. These are pretty far off. And I just kind of put these beautiful CT images of lunar grains to show that they're not spherical, and they're also they're not very smooth. You can see the plagioclase grain is kind of nice, but everything else is just kind of a big mix. So, and then there are lunar specific properties that we consider. So Larry Taylor did some work where they looked at the magnetic susceptibility of an orthocytes, because these are plagioclase grains that actually have iron metal particles in the rims. And it's true of the mature soils, it's true of the immature soils. So that's going to induce some bulk magnetic susceptibility into regolith samples. And then we also have to look at the agglutinates. They're really glassy materials that are created when impacts happen and melt everything, and then it cools too fastly to actually recrystallize. And so these are kind of properties that are important to us in lunar simulants. I think they're probably important when considering excavation and construction. No lunar simulant is one size fits all, as much as we would like to make them. They are a good approximation of what the moon is covered with, but they're not identical, and we have to make sure we're paying attention to those differences when planning experiments and simulations. Let me take a drink quick. So I just want to also point you towards 2 web pages there down there at the bottom. You can use your phone camera to look at those. There's a page on the public website that contains our evaluation from last year. Soon that will be replaced with a new evaluation that we're currently conducting right now. And then also the Confluence page. We've started a Lunar Simulants working group that we want to have people join and have conversations and discussions. The public webpage also includes a survey that I think would be useful for giving us feedback on what kind of simulants you're going to be looking for your experiments and your development, and you know, what particular, it'll help us know what particular properties we should be evaluating. And that's all I have. I'm happy to take any questions if we have time.